Next, in state variable analysis, we want to obtain the state diagram from a given transfer function. And this process of obtaining the state diagram from the transfer function is called as decomposition of the transfer function. So there are various methods in which you can do the decomposition. We will now discuss what are these methods. Okay. So the very first method is the direct decomposition. Here you can get either in the controllable canonical form or in the observable canonical form. Okay. So remember these abbreviations. It is difficult to write them over and over again. Alright. Next is the cascade decomposition. And finally, there is parallel decomposition. We use these methods depending on the transfer function that we have. Okay. Depending on transfer function, we choose the suitable method. So we will first start with the direct decomposition. Now what kind of functions we use direct decomposition? Okay. So the transfer function, usually it will be in the form of a numerator polynomial by the denominator polynomial. You don't have to factorize it. So that is b3 s cube. Let us take, we are taking a third order polynomial in the numerator, plus b2 s square plus b1 s plus b0 divided by s to the power 4 plus a3 s cube plus a2 s square plus a1 s plus a0. So this is only as an example. There can be higher order polynomials as well. Okay. So using this example, we will try to get the controllable as well as the observable canonical form. First, we will start with the controllable canonical form. So what is it abbreviated as? CCF. Now here the first step is to take the highest power of s. That is, either here we have the highest power as s to the power 4, right? If the highest power was in the numerator, then you can take that as well. Okay. So the highest power in either the numerator or the denominator you have to take, and you have to divide both the numerator and denominator by that term. Okay. So you can write down, the first step is to divide the numerator as well as denominator with highest power of s that is available. Okay. So here what we have, when we divide by s to the power 4 both the numerator and the denominator, what are we going to get? b3 s to the power minus 1 plus b2 s to the power minus 2 plus b1 s to the power minus 3 plus b0 s to the power minus 4 divided by 1 plus a3 s to the power minus 1 plus a2 s to the power minus 2 plus a1 s to the power minus 3 plus a0 s to the power minus 4. Next step is to take a dummy variable or a dummy polynomial. Okay. And you have to multiply that to the numerator as well as denominator. Okay. Multiply numerator and denominator of transfer function by a dummy function or a dummy variable x of s. Then what are you going to get here? The same function you are going to get, just that now you have x of s multiplied to the numerator as well as the denominator. And next step is to equate the transfer function. We know that it is the output function divided by the input function. This is the output and this is the input. But we just got this, we expressed it as this function, right? So now what you do is equate the numerator and the denominator respectively. So what are you going to get? Y of s is equal to b3 s to the power minus 1 x of s plus b2 s to the power minus 2 x of s plus b1 s to the power minus 3 x of s plus b0 s to the power minus 4 x of s. So you can take this as equation 1. Okay. And what about the other equation? You're going to get u of s is equal to x of s plus a3 s to the power minus 1 x of s plus a2 s to the power minus 2 x of s plus a1 s to the power minus 3 x of s plus a0 s to the power minus 4 x of s. From here, you can write x of s in terms of u of s and the rest of the terms. So what will you get? X of s is equal to u of s minus rest of all of these terms. So you can replace all of these plus with negative signs. Okay. So it will become minus, minus and minus. Okay. So now this equation you can take as equation 2. You can see that equation 1 is the output equation. Y of s you got in terms of x of s, and equation 2 is the state equation. From here you can draw the state diagram. Now we know that s to the power minus 1 indicates an integrator, and s to the power minus 4 you have, s to the power minus 1, 2, s to the power minus 2, minus 3, minus 4 you have. That means there are 4 number of integrators. So first you can draw 4 integrators. Okay, that you can take it as the first step of drawing the state diagram. So this will have a gain s to the power minus 1. Here the gain is s to the power minus 1, the third integrator and the final fourth integrator. Okay. Next, the variable x of s we can take here. Okay. So that what will happen to this variable, at this point node here, it will become s to the power minus 1 x of s. This node will become s to the power minus 2 x of s. This will be s to the power minus 3 x of s, and finally this is going to be s to the power minus 4 x of s. Now from the state equation you can see that x of s is equal to u of s minus a3 s to the power minus 1 x of s. So from s to the power minus 1 x of s you have a gain at minus a3. Okay. So from here to here you can join minus a3. Then what about s to the power minus 2x of s? Here you have a gain minus a2, right? You can see in this state equation here. So you will draw a gain here minus a2. Now from s to the power minus 3x of s, what was the gain? It is minus a1. Finally from s to the power minus 4x of s, it is minus a0. But one more term is left out in the state equation. What is that? It is the input function. So for input function, you can draw another path here which is having a gain 1. Okay. So we have drawn the state equation. Now what is left out? The output equation. So in the output equation, similarly you have y of s is equal to all of these terms. From s to the power minus 1 x of s, the gain is b3. So where is s to the power minus 1 x of s? Here you have s to the power minus 1 x of s. So the output you can draw somewhere here y of s. From s to the power minus 1 x of s, you have a gain b3. Okay. Then next, from s to the power minus 2 x of s, you have b2. Similarly, from s to the power minus 3, you have b1, and s to the power minus 4, you have b0. So you can draw here from s to the power minus 2, the gain is b2. From here, the gain is b1, and finally from here, the gain is b0. So this is how you can obtain the state diagram. Remember that here we have not considered the initial values. From here we can get the state model as well. Okay. So if you redraw the state diagram here we can remove these s to the power minus 4 x of s and everything, because x of s is not necessarily something that we require. We will have new state variables. The function of s of s, x of s, is only to obtain the state diagram. Okay. So now here we can take x1. Here we can take x2, x3, x4. And what we can take here? x4 dot. Okay. So it follows now that x4 is nothing but x3 dot, x3 is nothing but x2 dot, and finally x2 is nothing but x1 dot. Then what is x4 dot? x4 dot you can get from the state diagram. What are all the branches coming towards x4 dot? U is coming from x4, x3, x2 and x1. So x4 dot is going to be u minus a3 x4 minus a2 x3 minus a1 x2 minus a naught x1. Okay. So we here with these four equations we have the state equations, right? What is left out? The output equation. Output equation, y is equal to, y you have from x1 you have b naught gain coming, from x2 b1, x3 b2, x4 b3. So y you can write as b naught x1 plus b1 x2 plus b2 x3 plus b3 x4. This will comprise of the output equation. So now let us try to write in the matrix form. We know that x dot is equal to ax plus bu. Okay. So x dot will have x1 dot, x2 dot, x3 dot and x4 dot. Right. Now this is equal to, x1 dot is equal to x2 simply. So here you're going to get 0, 1 and rest of them will be 0. Right. X is x1, x2, x3 and x4. And what about input function? Will x1 dot depend on input function? No. So it will be u, 0. Okay. Now what about x2 dot? x2 dot is simply x3. So you're going to get 0, 0, 1 and 0. Here you're going to get 0. x3 dot is equal to x4. So you're going to get 0, 0, 0, 1 and here also 0. What about x4 dot? This is equal to minus a naught x1. So you will get minus a naught here, minus a1 x1, minus a2 x2 and minus a3 x4. And what about input function? Here you have 1. So this is indeed in the controllable canonical form, right? This is the form of A matrix should be like this in the controllable canonical form, and B matrix will be like this. Okay. Now what about output equation? Y you can write as x1, x2, x3 and x4 will be here. Now y is equal to b naught x1, b1 x2, b2 x3 and b3 x4. Then what about input function? It is not depending on input function, so simply 0 times u. So this is how you obtain the controllable canonical form, the state model as well as the state diagram. Next we will try to get the observable canonical form. What is this abbreviated as? OCF, right? So here the things will be slightly different. In step 1, what was the transfer function? Just write down the transfer function once again. The same transfer function we are taking. Okay. So what is that? b3s cube plus b2s square plus b1s plus b naught divided by s to the power 4 plus a3s cube plus a2s square plus a1s plus a naught. Now what is the step 1 here? Same as what we did in the controllable canonical form. You divide by the highest power of s. Then what are you going to get? You're going to get transfer function y of s by u of s is equal to b3 s to the power minus 1 plus b2 s to the power minus 2 plus b1 s to the power minus 3 plus b0 s to the power minus 4. Okay, and here you have 1 plus a3 s to the power minus 1 plus a2 s to the power minus 2 plus a1 s to the power minus 3 plus a0 s to the power minus 4. Now the second step is where we get all different. Okay, if you remember the Mason's gain formula, what was the Mason's gain formula? This was transfer function is equal to the sum of mi delta I by delta. Okay, so if you don't remember this, then just go back and you verify. Okay, otherwise it will not be clear to you. This method will not be clear to you. Okay, now if you compare this and this, you can see that in the numerator sigma mi delta I, if you equate to this, you have 4 terms. Okay, so that means you have 4 forward parts here. Comparing the transfer function with Mason's gain formula, you can see that there are 4 forward paths. So you can equate each of them. M1 is equal to, we will take for simplicity, delta 1 is equal to delta 2 is equal to delta 3 is equal to delta 4 is equal to 1 we will take. Okay, so just for making things simple. Alright, so that means if delta 1, delta 2 and delta 3 are all equal to 1, it means all of the loops, any loops if they are present, they are all touching each other. There are no non-touching loops. Okay, all loops touch forward path. So then M1 you are going to get as B3 s to the power minus 1, M2 is B2 s to the power minus 2, M3 is equal to B1 s to the power minus 3 and M4 is equal to B0 s to the power minus 4. Similarly, comparing the denominator, delta is what? 1 minus sum of all loop gains plus sum of all loops which are non-touching, 2 non-touching loops. Okay, but here what we will do, we will take all of the loops are touching each other, so that only we have 2 terms. Okay, so you can write here our assumption that all loops are touching each other. So we have taken 2 assumptions here. What are the 2 assumptions? The first assumption is that delta 1, delta 2, delta 3 and all, they are equal to 1. So that means this follows from the assumption that all loops are touching the forward path. This is assumption 1. And what was assumption 2? All loops are touching each other. Okay, that means there are no non-touching loops. Now comparing both the denominators, what will you get? Delta is equal to 1. So one term is here. All of the other terms you can take as the individual loop gains. But remember that you have a negative sign here. Okay, so you have to take minus a3 s to the power minus 1 will be 1 loop gain. Similarly, minus a2 s to the power minus 2 will be 1 loop gain. Okay, so you can write L1 is equal to minus a3 s to the power minus 1, L2 is equal to minus a2 s to the power minus 2, L3 is equal to minus a1 s to the power minus 3 and finally L4 is equal to minus a0 s to the power minus 4. Now we will see how to draw the state diagram. Here what you will do is, the number of integrators anyways, there will be 4 integrators because s to the power minus 4 is present. But now you will, between each integrator, you will keep a path of gain 1. Okay. So for example, this is s to the power minus 1. Here you have 1. And then only next you have s to the power minus 1. Okay. Similarly, this is going to be 1. Here you have s to the power minus 1 and finally another s to the power minus 1. Okay. So now you have 4 integrators. Between each of these integrators you have a path of gain 1. Okay. Now the input function somewhere you can take here u of s, and output function you can take somewhere here y of s. Now how each of them will be related? Now we get from this information that we got here. Here we have 4 paths. These are the forward path gains. That means from u of s to y of s there are 4 different forward paths. Okay, and each of them will have the respective gains like this. So now if you take the first path, b3 s to the power minus 1 should be the path gain. It has only one integrator, s to the power minus 1. So what we will do is from u of s to this we will take the gain b3, and from there you have one gain, let us say. Okay, so now this is one forward path, right? What is the gain of this forward path? b3 s to the power minus 1. Now what about second path? b2 s to the power minus 2. So now you need 2 integrators. So you can draw a gain like this. So this is going to be b2. If you want 3 integrators in the forward path, then you're going to draw here. This is going to be b1. And finally here you can draw b0. So what will be the path gain of this forward path transfer function? b0 into s to the power minus 1 into s to the power minus 2. Like that, b0 s to the power minus 4 you are going to get. Now we have drawn all of the forward paths. Now what about the loops? You see the first loop here, it is minus a3 s to the power minus 1. So we can take this integrator here, which is towards the output side, and we can draw a path like this, the gain of which will be minus a3. Okay, so now this is a loop, and what is the gain of this loop? Minus a3 s to the power minus 1. Now what about the second loop? Minus a2 s to the power minus 2. So we need to take 2 integrators. Okay, so now this is going to be the second loop. Okay, you can see that these are both touching each other. They are not non-touching. Okay, similarly L3 you can draw like this. Okay, so this is going to be minus a1, and finally the last loop you are going to have the gain is minus a0. This is how you get the state diagram. What is the next step? From here you have to get the state model, the dynamic equations. Okay, so step 4 is to obtain state model, and here you will see that it will be in the observable canonical form. So we will see how to do that. The trick is to choose the state variables correctly. Okay, if you remember, in the controllable canonical form we took x1 here, x2 here, and x3 and so on in this direction from right to left, right? But now what we'll do, we'll start taking x1, x2, x3 in the opposite direction, that is from the left to right. Okay, so what we will do here is x1 we will take here. What will be the point here? x1 dot, right? Because s to the power minus 1 is integration. So if you are integrating x1 dot, it means that you are going to get x1, right? So x1 here, x1 dot here. Similarly for this integrator, on the output side you will take state variable x2, on the input side you will take x2 dot. So this is x2, x2 dot. Here again x3, and here x3 dot. Finally here you will have x4, and this is going to be x4 dot. Now here this input and output we will take in terms of the time domain. Okay, so this is going to be u of t, and this is going to be y of t. Now we can write down the equations. First we will find out state equation, right? We know that x dot is equal to ax plus bu. So we will first start with this. What is x dot? It is x1 dot of t, x2 dot of t, x3 dot, and x4 dot, because there are 4 state variables here. So first if you write the equation for x1 dot, What will this be? In the state diagram, you can see there is one path coming from u of t and another path coming from x4. Is there any other path that is the ending here at x1 dot? Only these two paths. So we can write x1 dot of t is equal to minus a naught x4 plus b naught u. Okay, so I have written the state variable first because we have ax plus bu. Okay, input function we will write later. Similarly, x2 dot is equal to, here from the state diagram you can see one is coming from x1, one path is coming from x1, another path is coming from u of t and another path from x4. So x2 dot is going to be equal to x1 minus a1 x4 plus b1u. Similarly, for x3 dot you are going to get x2 minus a2 x4 plus b2u. And finally, x4 dot you are going to get x3 minus a3 x4 plus b3u. Okay. So from here you can get A and B matrices. This means that x1 dot, x2 dot, x3 dot and x4 dot, this is going to be equal to, here you can write x1, x2, x3 and x4 plus b into u. So what will be the first row of this A matrix? Here you are going to have, there are no relation with x1, x2, x3. So you are going to get 0, 0, 0. With x4 you have minus a naught. Okay. And x2 dot you have a relation with x1 and x4. So this is going to be 1, 0, 0 and minus a1. x3 dot you are going to get 0, 1, 0 minus a2. And finally x4 dot is going to be 0, 0, 1 minus a3. Okay. So this A matrix is in the form that we had discussed in the observable canonical form. Right. Then what about B matrix? This is going to be B naught, B1, B2, B3 into U. Okay. So this is the state equation. Next, what about the output equation? Output equation, once again you will have to see from the state diagram. So y of t, you can see only one gain is coming, path is coming from x4. So y is simply equal to x4. So you can write here the output y is equal to, here x1, x2, x3 and x4. Now y is only related to x4, it is equal to x4. So all of the x1, x2, x3 relation will be 0, x4 will be equal to 1 plus 0 times u. Okay. So you can see that here we have the A matrix, here we have the C matrix. These are in the form as discussed in the observable canonical form. Okay. Now what is this equation? It is the output equation. Before we discuss about cascade decomposition and parallel decomposition, we will use the direct decomposition to get the state diagram of a first order function. Okay. So direct decomposition of first order function. So take it like an example, but we will be using this while discussing the cascade and parallel decomposition. So there are two kinds of first order functions that we will be discussing. First is of the form s1 plus b divided by s plus a. Okay, so that means you have a first order polynomial in the numerator as well as denominator. In the second case, we will discuss only a first order polynomial in the denominator. Okay, so first we will go ahead with this. We will use the procedure that we used to obtain the observable canonical form. So in that, what we did, transfer function is equal to s plus b by s plus a. We have to divide by the highest power of s. So here it is only s to the power 1. So you're going to get 1 plus b into s to the power minus 1 by 1 plus a into s to the power minus 1. Now this, if you compare with the Mason's gain formula. What is it? Sigma m1 delta 1 by delta. So here you have two terms in the numerator, so you have two forward paths. What will be the paths? m1 is equal to, here we will always assume delta 1 is equal to delta 2 is equal to 1. That means any of the loops will be touching the forward paths. So m1 will be equal to 1, m2 will be equal to b s to the power minus 1. Then what about the loops? There will be only one loop, and what will be the gain of that? Minus a s to the power minus 1. Now we can start drawing the state diagram. So there is only one integrator, so we will draw one integrator first, s to the power minus 1. Now the input function we will mark here, and output, let us say it is somewhere here. Now one forward path is having a gain of b s to the power minus 1. So let us take a straightforward path. Here you can take 1, and here you can take b, and finally you can take 1 here. Now another forward path will be having a gain of 1. So it will just skip this part, b s to the power minus 1. And what will be the gain here? 1. So now you have two forward paths. This is one forward path whose gain is b s to the power minus 1. And the second forward path is like this, whose gain is 1, simply 1. Okay. Then what about the loop L1? It is having minus a s to the power minus 1 as the gain. So you can draw the loop like this. This is minus a. So now this loop is touching both the forward paths. Okay. So all of the rules are satisfied, all of the assumptions are satisfied. Now this is the obtained state diagram. So whenever you have a function like this, s plus b by s plus a, then you will simply use this state diagram. You can remember it. Once you practice, it will become easier to remember it. Okay. Now what about the next case? Case 2, we have 1 by s plus a. Now in a similar way we have to do. The transfer function is given by 1 by s plus a. So we will have to divide the numerator and denominator by the highest power of s, which is s to the power minus 1. So you're going to get s to the power minus 1 divided by 1 plus a s to the power minus 1. Okay. So from here what will you get? There is only one forward path whose gain is s to the power minus 1, and the loop gain is minus a s to the power minus 1. Okay. Now what will be the state diagram? You can draw one integrator, no difference here. Now the input function you can draw here, output function you can draw here. Since the forward path gain is only s to the power minus 1, you can just draw paths of unity gain here. Okay. Then what about the loop? The loop is having a gain of minus a s to the power minus 1. So you can draw a loop here. This is minus a. Okay. As simple as this. Right. This is one loop and it is touching the forward path. So if you get the Mason's gain formula for this, then you're going to get this form. So this is the required state diagram for functions of the form 1 by s plus a. Okay. Now let us discuss cascade decomposition. Once we have seen how to direct decompose a first order function, then cascade decomposition is not very difficult. We choose cascade decomposition whenever the transfer function can be factorized. Used when transfer function can be factorized. So what will be the form of this kind of transfer function? Y of s by u of s will be equal to some k we can take as the gain into s plus b1 into s plus b2 divided by s plus a1 into s plus a2 into s plus a3 we can take, just for the example. Now the very first step that we can do is rewrite the transfer function as product of different terms. Okay, so that means you can write transfer function is equal to k into s plus b1 by s plus a1 into s plus b2 divided by s plus a2 into 1 by s plus a3. Now we know that whenever you have cascaded transfer functions, let us say this is g1 and g2, then what will be the transfer function? g1 into g2. Similarly, here you have product of different transfer functions. So you can consider this to be transfer function 1, this is transfer function 2, this is transfer function 3, and this is transfer function 4. Then how can you write? You can draw all of these blocks in cascade. Okay, so that will be transfer function 1, transfer function 2, similarly transfer function 3, and finally 4, right? So here you will have the output and here you will have the input. Now each of these transfer function blocks, if we know, then we can replace these blocks with the actual transfer function. Okay. Similarly, signal flow graph. If you want to draw in signal flow graph, then how will it be? It is going to be like this. Here you have transfer function 1, 2, 3 and 4, right? So you can add an additional 1 gain so that you can write the input and output here. Now for these kind of transfer functions, we have already derived using direct decomposition. We have found out what is the state diagram representation of these kind of transfer functions. So that will be the second step, step 2. Okay. So what will be the transfer function 1? This is simply the gain k, right? This is k, input and output. Now what is transfer function 2? This is s plus b1 by s plus a1. So how did we derive this? There was one integrator s to the power minus 1. You have the gain b1 here, the loop gain minus a1, another forward path, this will be 1, and finally input, this gain is 1, and here you have the output. Okay. So this is what we derived using the direct decomposition. Now next, what about transfer function 3? This is the same form as transfer function 2, right? Instead of b1, a1, you have b2 and a2. Okay. So now it is going to have the same form, except that instead of b1 and a1, you are going to write b2 and minus a2. Then finally, what about transfer function 4? This was 1 by s plus a3. So here you had one integrator and the gain minus a3, and on either sides you have a paths of gain 1. This is the input and this is the output. Now from here you can draw the complete state diagram. The input, actual input will start from here, and from here we will just draw a straight line here. The first gain will be transfer function 1, which is k. Okay. Next we have transfer function 2, which is 1 we have here, integrator s to the power minus 1. This will be b1. Here you are going to have minus a1, and here you have a forward path of gain 1, right? Next you have gain 1. Now transfer function 3 starts. Okay, so we can consider this one as part of transfer function 3 as well. We don't need two gains of two paths of gain 1, right? So we will get s to the power minus 1 here, and here you are going to have b2. Here you are going to have minus a2, and this is going to be the forward path of gain 1. And finally the last transfer function, this is the integrator s to the power minus 1, and you are going to have gain 1 here. Okay. So this anyways it is not required now. Okay. So also you have the gain here, loop gain minus a3. and this is going to be the output. You can represent each of the transfer function. This is transfer function 1 and here you have transfer function 2. Here you have transfer function 3 and finally this is the transfer function 4. All of them, they are in cascade. So this is how you will complete the state diagram when it comes to cascade decomposition. Now what is left out? You have to find out the state model. For that you have to choose the state variables. So we have redrawn the state diagram once again. Now the state variables we will take as for each of the integrator, the output side of the integrator we can take as a state variable and on the input side we can take as x dot. Okay. So that means if you take x1 here, then x1 dot will be here, x2 here, then x2 dot will be here, x3 here, then x3 dot will be here. Okay. Now you have to write down the state equations. What are state equations? State equation and output equation. You need to write both. Okay. So we will start with the state equation. So x dot is equal to ax plus bu. What is x dot here? It is the state vector x1 dot, x2 dot and x3 dot. So we will first write down the equations for each of these variables. Okay. So what will be x1 dot? You have one path coming from here, another coming from here. Okay. But here you need a variable to express it, right? So we will take additional variables here, y1 and y2, but in the final expressions we don't want this y1 and y2. Okay. So you can write x1 dot is equal to y1 minus a3 x1. Now what is y1? It is coming from x2 and x2 dot. So we need to first know the expression for x2 dot. Okay. Similarly, to find x2 dot, we need the expression for x3 dot. So what we will do is, we will start writing the equations from x3 dot. Okay. So what will be x3 dot? Here you are getting one path from here, another path from here. So this is going to be the input function you can write as u and output function you can write as y. So x3 dot is going to be minus a1 x3 plus k times u. This is the first equation. Now x2 dot, what is it equal to? Minus a2 x2 plus y2. This is going to be minus a2 x2 plus y2 you can write as b1 x3 plus x3 dot. So the final expression you're going to get x2 dot is equal to minus a2 x2 plus b1 minus a1 into x3 plus ku. This is the second equation. Similarly, you can write x1 dot. I'm writing the final expression you're going to get minus a3 x1 plus b2 minus a2 into x2 plus b1 minus a1 into x3 plus k times u. Okay. So now you can write down the state equation. What will it be? x1 dot, x2 dot and x3 dot will be the 1 matrix. And this is going to be the A matrix. Here you're going to get x1, x2, x3 plus b times u. There is only one input. So you will have a column matrix here. B will be a column matrix. So now what will be A matrix? Here you're going to have x1 dot, you can see minus a3 x1. So minus a3, x2 is b2 minus a2 and x3 coefficient is b1 minus a1. What about x2 dot? It is no relation with x1, minus a2 x2, b1 minus a1 x3. What about x3 dot? 0, 0 minus a1. Okay. What about matrix B? All of them will be K. So this is matrix A and this is matrix B. This is what? The state equation. you can write the output equation next. Okay, so what will be, you have to write the expression for y. Y is simply equal to x1. Okay, so the here output equation is simple enough. Output y is equal to x1 implies that you can write in the matrix form. This will be C matrix, x1, x2 and x3 plus, it is not related to the input, so you can write 0 u. What will be the C matrix here? Y is equal to x1, so coefficient of x1 will be 1, others will be 0. Okay, so here this is going to be matrix C and this is matrix D. Okay, so this is how you obtain the state model in cascade decomposition.